Hey, this is Leach with Sims of Math, and in this video, we're going to be looking at how to apply some context to our normal model questions. Specifically, this is directed towards my contemporary math students, my current students, or unless future me has changed the problems. This should cover questions 17 through 21 in section 12.5. All right, so let's take a look at this. So this is a certain dry cereal is packaged in 14-ounce boxes. The machine that fills the boxes is set so that on average, a box contains 14.2 ounces. The machine-filled boxes have content weights that can be closely approximated by a normal curve. What is the probability that a randomly selected box will be underweight? That is, the net weight is less than 14 ounces if the standard deviation is 0.4 ounce. They give us the tables. I would not use the tables. They hurt my brain. I can imagine what they do to you. We're just going to be using technology, specifically Desmos. So this is if the standard deviation is 0.4 ounce, what's the probability of a box being underweight? And we're going to find that. I'm going to first draw a picture of this. So here I have a blank normal curve. Just to be clear what's happening, I'm saying that the mean is 14.2. Let me make that a bit clearer. 14.2 ounces. And the standard deviation is 0.4. And I want to see where 14 would fall. Well, if I go down one full standard deviation, this would be at 14.2 minus 0.4, which would be 13.8. So this right here is 13.8, which is definitely underfilled. So we're actually kind of going to aim for about really halfway between these two is probably the z-score of interest, is probably the location that we're looking for. There's our 14.0, and I want to find that the likelihood that we get something down here. But you can see that's a pretty big area. From our empirical rule, we know that this is going to be more than 16, because if I'm at -1 or less, that's 16, but not quite the 50. I know that the answer you saw a second ago was about 30%, and so let's use Desmos to check that out. All right, so again, you can pop open the keypad functions, scroll down, and pick normal distribution. I'm gonna just do the inference way. So click on inference, click on probability distribution, pick on the normal distribution. We have a mean of 14.2. I'm pressing tab on my keyboard. Standard deviation of 0.4. And then press create distribution. It even zooms it over if for some reason you mess it up or you zoom out. Just press zoom fit and you'll get back to where you want to be so you can see it. I want to find the area less than 0.4, so let's toggle open cumulative probability. It defaults to enter an area, which is fine. We want area less than, we want it to be underweight, so if it's underweight, it would be less than 14, so we're doing a left option. And I do want to compute the area instead of a bounds. My input's going to be a weight. My output's going to be the probability. So my input's going to be the weight, which is going to be 14. And my output's going to be the area, which is the 0.309, which is my answer right there to the nearest thousandth. Again, if I wanted more decimal places, I can just toggle open to get more decimal places. So 0.309. It does give you a little bit of wiggle room because of rounding things, especially if using a table, and that is likely to happen. All right, so again, let me talk through those steps. So I opened up a new inference, did a probability distribution, left it at the default normal. My mean was 14.2. My standard deviation was 0.4. And I want to find the area less than, so I toggle open cumulative probability, keep it at area, but change it to left, and put in my left of what? Left of 14. And that's how we get our answer. All right, the mean clotting time of blood is 7.45 seconds. The standard deviation, 3.6 seconds. What is the probability that an individual's clotting time will be less than 6 seconds or greater than 9 seconds? Assume a normal distribution. So I could go back to that top screen, the create an inference distribution, put in the mean and standard deviation. I'm just going to want to prove the point that I can edit it here. If I delete out these two numbers from the last question, I can put in my mean of 7.45. Notice it's defaulting to standard deviation of 1. It says standard deviation 1 right here. I'm going to go ahead and put comma. That equals 1 goes away, but in my, what is this? Desmos breaks a little bit. It's like, hey, you need something there. Like, yeah, it's going to be 3.6. I'm going to press zoom fit to zoom into where I want it. It is leaving up my last problem because I haven't deleted it. So it's still at the less than 14, which is fine because I'm going to change the problem. So I want to find the area less than 6, greater than 9. I could do a less than and then do a greater and then add. So a left and then a right and then add. Or I'm just going to go ahead and do outer. So I want less than, x is less than 6. So delete the 14 and put in a 6. Or greater than 9. Less than 6 or greater than 9. And so when I do that, I get 0.677. If I wanted to find them individually, I could do less than 6, and I would get this 0.3444. Let me go ahead and export that number. Greater than to the right of 9, and I get 0.33957. That's not 1/3. And if I add those two numbers together, so this number plus this number, oops, I deleted it. I get this 0.67677, which when I do my outer, less than 6, greater than 9, is our decimal value there. Right. Just going to go ahead and delete this all out so I get a fresh start. A teacher gives a test to a large group of students. The results are closely approximated by a normal curve. The mean is 76 with a standard deviation of 5. I'm going to go ahead and jot that down. This one hurt my brain one of the first times I looked at this. So let me get rid of all this so I can start from scratch. So the mean is 76 with a standard deviation of 5. The teacher wishes, so this question I wish was a little bit clearer. This teacher is producing a curve. Some ways that some teachers will curve their tests is they force a bell curve to happen. So they want, in this case, they want the top 8% of students to have an A. They want the bottom 8% of students to have an F. They're just kind of forcing it to fit into a bell curve, which, I don't tend to do it this way, but some people do. The bummer when people follow this is if it was an easy test and lots of students basically natively made an A's and B's, they're going to still force the bottom people to have an F. That's less than fun for some students, but that's what this is happening. I think no one's going down. I think when I looked at this a second ago, everyone's grade is typically moving up. All right. So the teacher wishes to give A's to the top 8%, but F's to the bottom 8. Then B's to the next 15%, and similar to D's, and the rest get C's. So what's happening here is wherever the top 8% is, yes, they might have, we're not concerned about what their numerical grade is. We're just going to be like, you get A's. So they're going to, they'll get an A for that test. So we want to know where the bottom cutoff is for B. So I mean, put this into Desmos. So this is the grades about what's happening. I want to find where the bottom 8% would be about here. If this is 8%, everyone here and above is going to get an A. And then let's make that say an 8. Then there's another kind of amount. It's about like here or so, where this is 15%. This region here is 15. And so that would be those who get a B. And we want to know what would that grade with the bottom cutoff for those who get a B. In this case, the answer is going to end up being read at a B. An 80 gets a B, which is not always the case. All right, so let's put this in. So I'm going to do inference, probability distribution, leave the normal. My mean is 76. My standard deviation is 5. And I want to find basically I'm going to add these two things together. 15 plus 8 is 23. So I need to find the cutoff for the top 23%. So I want to go to the right. This time I'm computing the boundary for the top 0.23. So the top 0.23 is at 23%. That is the 8% plus the 15% for the B. And so when I do that, I get rounding to 80, but 79, 69. So in this case, those who made a 79, 69, they made a B or better. I'm going to do a similar question just to show you one that it's not 74. So what just changed was it's 71 was the mean with a standard deviation of 4. So just change this as a new question, new numbers, but same question. And it's still 8% and 15%. So this is still the top 23%, just so happens. Still top 8 B's are the next 15%. So the top 23% made a B, make a B or better. So this would be, if you made, in this particular case, if you made a 74, then you would make a B. Just for clarity, if you were to make in the top 8%, 0.08, for the students who made a 76.62 or better, they would end up with an A on the exam. The next question is very similar to the one we just did, but we're finding the cutoff for the D's. So this one we have a mean of 78, standard deviation of 6. Let me make that edit. Mean of 78 with a standard deviation of 6. The A's to the top 7%, F's to the bottom 7, B's to the top 15, D's to the next 15. So in this case, it's going to be bottom 7 plus bottom 15 would be 22%. But since it's a D, I'm going to do the cutoff from the left. Let me draw that picture. All right, so we're at 78. The mean of 78, standard deviation of 6. So somewhere down here, about, that'd be 2.5. So about here or so, when that's 7%, everyone who is at that 7% or less would make an F. Just for clarity, that would be those who made a 69.15 would end up with an F on this exam. So their average actually, their grade actually would be lower than this. It'd be bumped down to a 60 or something like that. But the D's would be the next 15%. So there's some section about here that's another 15%, or in total, a 22%. And those would be those who get the D's. So I'm going to put in a 22 here, 0.22. And we get that's a 73 here. Why is that? Oh, bottom cutoff. Oh. Bottom cutoff for D's. This 73 is the top cutoff for the D's. So, but I want the bottom cutoff, which is what I had on the board a second ago, which is the 0.7. So those who made a 69 or better would make at least a D. Those who were under 69 would make an F. So because it's the bottom cutoff for the D, that'd be 69. The top cutoff for the D would be the 22 that I just did, which would be a 73. So those who made between 69 to 73 ended up making a D on this exam. All right, last one. A manufacturer makes carts with industrial swivel rollers that must support a load of at least 110 pounds. Supplier A can provide rollers supporting 115 pounds on average with standard deviation 2.1. Supplier B's rollers will support 120 pounds on average with standard deviation 3.6. Complete these parts. If both distributions can be assumed to be normal, which supplier offers a smaller percentage of unsatisfactory rollers? We'll answer it. This says it's B. We'll find out why and give you a reasoning. So what I want to do, I'm going to put in both of these normal distributions and find the area that's less than 110 because it needs to be at least 110. So if it's heavier than it needs to support everybody at least 110. But if they at least 110, at least hurts my brain. At least, yeah, okay. So I'm going to put in our inference probability normal 115 with the standard deviation of 2.1 at least. That's the lowest. Oh, it will, okay, yeah. There's our first one, that's supplier A. And then I'm going to go to move my cursor to the second row and go ahead and do this again, but with a mean of 120 and standard deviation of 3.6. So we can see here that A is here in red, B is here in blue. B is higher on average, but it is less consistent. Because it's less consistent, maybe it's not as valued. So it must support a load of at least 110 pounds. And so if it doesn't support, so I'm going to find where 110 is here on both of these. So I'm going to do an area less than on both of these and put in the 110. Oops, too big. And we can see if I turn off the blue, we can see the red here, this shaded red right here. If I turn on the blue and zoom in on it, and we turn off the red, it's shaded is there, but it's a whole lot smaller. So if it's at least 110, so for some reason we want it to be more, this at least is hurting my brain, but basically we don't want it to be, oh, okay, yeah, they make these rollers, these things that will support it, and if somehow that particular roller falls in, like it will break at something that is over one, it would break if this is the breakage point of the, this is like the maximum load of those rollers. And if you get one that is a little bit weaker, basically manufacturer A, red is producing a broken roller about 1% of the time, or that would break at 110, 1% of the time. And then blue is producing a roller that would break about 0.3% of the time. So that's why the blue, the B1 is a little bit better. So we can see here the probability of an unsatisfactory roller from supplier A is 0.009, that shaded region there. The probability of an unsatisfactory roller from B is 0.003. So 0.003 both has a higher average. It is a little bit more inconsistent, but except for it for being a higher average, which ultimately has a lower failure rate of that at least 110. All right, that at least is hurting my brain a little bit, but it's that particular roller, this random distribution is that particular roller, and that particular roller is like kind of maximum breakage point. And so red would have a whole lot more, would have about 3 times as many breakages, breaking points at or below that 110 than blue. All right, that kind of hurt my brain a little bit. That's why I want to make sure to go over these with you. Hope this helps. I'll catch you in the next one. I think I have one more to do for this section.